Okay, so constant coefficient autonomous systems. This is a little bit of a review of things that we did in Math 327. So an autonomous system of equations has two or more differential equations where the independent variable does not depend, but does not appear on the right side. So here the independent variable is t, right? And x and y don't, these differential equations don't have t appearing explicitly in them on the right-hand side. So if we think of x and y as being animals, and t as being time, x and y are different animal populations, then the animal populations depend only on the rate of change of the animal populations depends only on the current size of the animal populations and not the time, right? So rate of change of the x animals depends only on how many x animals there are and how many y animals there are. So we can solve this system as using eigenvalues and eigenvectors. This is a nice linear system. Can rewrite it as, if I set capital X equal to the vector x of t, y of t, then this system becomes the derivative of the vector x of t equals m times x of t, where m is the matrix of coefficients from up here. So 6 minus 15, 2 minus 7. And the solutions to this system of equations depends on the eigenvalues and the eigenvectors of the matrix M. So eigenvalues, how do we find those? We take the determinant of the matrix minus lambda I2, we set it equal to 0. So I2 is the identity matrix, 2 by 2 identity matrix. So what this means is that I want to take, in practice, the determinant of the matrix where I take 6 minus lambda minus 15, 2 minus 7 minus lambda. So I take the variable lambda and I subtract it off from the main diagonal and I set that equal to 0. Now the determinant of 2 by 2 matrix is these two multiplied together minus these two multiplied together. So I get minus 6 minus lambda. And do I actually want a minus 6? No, I want a plus 6. It should be a plus 6. Times minus 7 minus lambda plus 30 equals 0, right? Because this is a minus 30, but the determinant also is a minus. So it's minus minus 30. And if we multiply this out, we get a lambda squared plus 7 lambda minus 6 lambda, which is a plus lambda minus 42 plus 30 equals 0. Or lambda equals lambda squared plus lambda minus 12 equals 0, which we can factor. Lambda plus 4, lambda minus 3 equals 0, lambda 1 equals minus 4, lambda 2 equals 3. So these are our eigenvalues. Once we find the eigenvalues, we want to find the eigenvectors. And eigenvectors are solutions to that equation, right? And the eigenvalues, lambda equals minus 4 and lambda equals 3, are exactly the numbers that make the determinant of the matrix m minus lambda I2 equal to 0, which means that we have non-zero solutions to this equation here. So if we plug in lambda 1 equals to minus 4, when we plug it into this matrix, we get 6 minus minus 4 minus 15, 2 minus 7 minus minus 4, xy equals 0, 0. So that's the matrix equation that we want to solve for x and y, and that'll become our eigenvector. 6 minus minus, that's 10, minus 15, 2, minus 7 plus 4 is minus 3. And that's good because at this step, we always want our two rows in our matrix after we plug in an eigenvalue to be multiples of each other. And we can take either the first row or the second row. We can take 2x minus 3y equals 0, set x equal to 3, y equals to 2, and that gives us an eigenvector. So eigenvector v1 is 3, 2. Okay. And if we take lambda 2 equals to 3, we do the same sort of thing. We get now the matrix 6 minus 3 minus 15, 2 minus 7 minus 3, x, y equals 0, 0. Right? And that becomes 3 minus 15, 2 minus 10, x, y equals 0, 0. And so I'll take again the bottom row, 2x minus 10y equals 0. And I can take x equal to 5 and y equal to 1. And so that gives me v2, comma, v2, the eigenvector that goes with lambda 2 equals 3 as being 5, 1. And the solution to this is x of t is k1 e to the minus 4t times v1, which is 3, 2, plus k2 e to the minus plus 3t times 5, 1. And k1 and k2 depend on what your initial conditions are. You can remember that having one of each of these, one positive, one negative, means that we have a saddle. So this is a little reminder about how to solve these things with eigenvalues and eigenvectors. This becomes important when we're trying to localize nonlinear systems. We can also try and sketch the system using null clines. So dxdt is 6x minus 15y. Let me just rewrite that down. And dy dt is, going back up, 2x minus 7y. So the null clines set x prime equal to 0, and then find the sign of y prime along that curve. The null cline for y, set y prime equal to 0, find the sign of x prime along that curve. So the idea is that we're looking for places where my velocity vector has no x component, and we're also looking for the places where the velocity vector has no y component. So x prime equals 0 means that 6x minus 15y equals 0, which means that 15y equals 6x, which means that y equals 6 over 15, which is what, 2 over 5? Right, so that's the null cline, right? Along this line, no horizontal component to my velocity vectors. Okay, so what is the vertical component? Well, that's y prime equals 2x minus 7y, which is 2x minus 14/5 x, because we can plug this in for y here, and we get minus 14/5. x2 is 10/5, so this is minus 4/5 x. In particular, when x is positive, this is negative. When x is negative, this is positive. So now we can try and start sketching our solution curve a little bit. Not our solution curve, our vector field. So y is 2/5 x. 1, 2, 3, 4, 5. 1, 2. 2/5 x has a slope of this, more or less. So all along this line, there's no horizontal component to my arrows in my vector field. There's just a vertical component. The vertical component is down for positive x. So my arrows look something like this. And my arrows are positive for negative x. So my arrows must be something like this. Great. So I can do the same sort of thing for the y prime equals 0. Where am I going to have a line where the arrows are pointing only left or right? So y prime is 2x minus 7y equals 0. Or y equals 2/7x. So along that line, there's no vertical component to my arrows. And so what's the horizontal component? Well, x prime equals 6x minus 15y. So that's 2/7x, because that's what y is. And so I get 6 42/7 minus 30/7. 12/7 x. All right, so this is 30, and 6/6 is 42/7. So I get 12x as my horizontal component. And note that this is positive for x positive and negative for x negative. 2/7, 1, 2, would be a line that comes out about like this. More or less. And my arrows point to the right here. And to the left here. The null line split the plane into 4 regions, one up here, one in here, one down here, and one down here. Arrows here have to be going down and to the left, because on this null line they're going to the left, and this null line they're going right. In here we have to be going up and to the left. In this region down at the bottom we have to be going to the right and up. And down in this space here we have to be going down and to the right. So the arrows point in those directions. We know that there should be one of our eigenvectors is 5, 1, and the other one is 3, 2. So 1, 2, 3, 2. That's one of my eigenvectors. It's here. That's an eigenvector. 3, 2 goes with an eigenvector of -4. And I know all the arrows have to be pointing into the origin along that line. And the other eigenvector is 5, 1, and that goes with lambda 1 equals 3. So 1, 2, 3, 4, 5. 1 is about here. So I have bad choice of numbers, I guess. My eigenvector going out here. So solution curves. If I started up here, I'm going to come cross this horizontally and head out. If I start up here, I'll come down and just head out along this thing. If I come up here, I will come up and now tangent along with this eigendirection. And then if I come up this way, this is my eigendirection here, my eigensolution. I can't cross that, so I'm going to come up vertically through there, go up to the left, horizontally through here, and out along that. And so that gives me my picture of my saddle. So the null-lines aren't particularly important when we're dealing with linear constant coefficient systems like this, because you can just do everything with eigenvalues and eigenvectors. But they will become important when we do nonlinear systems. We can also sketch this with Maple. So let me see if I can switch my sharing without too much interruption. Where's my Maple gone? Here it is. So this is Maple, and this is how we can sketch things. So in doing Maple, you need a couple of different things to be able to access all the things for solutions of differential equations. One is with plots, and that gives you lots of commands that you can use to plot things. So this is a package, the plot package that you have to load. With DE tools, this gives you lots of tools for sketching things with differential equations. And then plot tools also allows you to plot things with plot tools. So these are just packages that you have to upload into Maple, and with name of package in parentheses is the command. So this is our differential equation. Here's how you can enter it in. I've defined it. I gave it a name, LIN for linear. Colon equals, that's how Maple defines things if you want to name something. So LIN refers to whatever this object is. And it's a set of two differential equations. That's why it's in a parentheses, because it's a list of two differential equations. The first one is diff, stands for derivative of x with respect to t, is 6 times x minus 15 times y. And the derivative of y with respect to t, that's dy dt, is 2 times x of t minus 7 times y of t. You need to tell it explicitly that x and y depend on t. So DE plot, you tell it your the name of your system, which was Lin. That's the name of this particular system. And we want x of t, y of t. Those are our variables. And we set t running from -3 to 3, x running from, I actually want it to go from -6 to 6. And y going from -6 to 6. It's usually a good idea to keep your graph, the plot that you're doing, sort of square, right? -6 to 6, -6 to 6 for x and y. There, and there's our picture of it. This is the initial condition. It's in a double bracket because it's a list of lists, but the problem is this is a list of just one thing in the list. And the arrows, you can make them different sizes. And so here is a solution that starts at 1, 0.25, right? And so it's coming in along one of our eigenvectors and out along the other one. You can always change your initial conditions. You can ask for the initial condition that starts at 0, x equals 0, and y equals 1, right? And you get a different initial condition. So what we want to actually see is we want to see all 4 of the eigensolutions plotted so that we can see what's going on there. And that's what this is. So same, going to name it Fred, is the DE plot of my linear system, x of t, y of t are my functions, t going from -3 to 3, x going -6 to 6, and then I have a list of 4 initial conditions, 3, 2, -3, -2, that's one of my eigendirections, 5, 1, and -5, -1. That's the other eigendirection. And that gives me my saddle, right? Everything up here is going to go this way. Everything in here slides out this way and then that way. And we can put in the null clines, right? So again, I'm going to name it null draws. And it's just the plot of the two functions, 2/5 x, 2/7 x, running from -6 to 6 and y from -6 to 6. And I'll make the first one black and the second one blue. So the black one is the X null Klein. So there's that. Why did I name both of these? This is named Fred. This is named null draws. I've got two different pictures. The command display puts them both together, and there's our picture. And so here's the yellow curves are the eigenvector solutions, one coming in, two coming in, one up in the first quadrant, one in the third quadrant, and two going out, one in the first quadrant, one in the third quadrant. And then all along the black line, although it doesn't really look it, all the vectors are actually vertical. And all along the blue line, all the vectors are horizontal. And so that gives me my null Kleins for that. Again, the null Kleins aren't super useful for this particular case, but they come in very important when we start doing nonlinear systems. Okay, going back to the text. Here we go. So generally, when we have a system of this form, right? So it's nice and linear. There's nothing fancy going on here. We just have four variables. Find eigenvalues via determinant of A minus lambda, B, C, D minus lambda equals 0, or lambda squared minus trace lambda plus determinant lambda. Lambda. Sorry about that. Let's see if I can undo that instead of just scribbling it out. Trace of M times lambda plus determinant of M equals 0. So M is the matrix. The trace of M is just the sum of these, of the main diagonal, A plus D. The determinant of M is equal to A, D minus BC as usual. And then find eigenvectors, not eigenvalues, eigenvectors for each eigenvalue. Because this turns out to be a quadratic, look at the lambda squared, complex eigenvalues have complex eigenvectors, and we're not going to worry about those too much. The complex eigenvectors aren't particularly interesting for us, right? We're interested in the case where our eigenvalues are real and they each get their own eigenvector. But there's something called the Parquet diagram, which is this thing, classification or phase portraits in the determinant A trace A plane. So here's the trace of our matrix. Here's the determinant. The discriminant is b squared minus 4ac. It's the thing inside the square root of the quadratic formula. If that's negative, if you get a complex number, you get spiral sinks or spiral sources or centers along where determinant A equals 0. If determinant is equal to 0, that's where you get, well, they call it a degenerate source or degenerate sink, but this is where you have a repeated eigenvalue, and you get things that look like this. And then delta is greater than 0. You could have a source if your determinant is greater than 0, or a sink, determinant greater than 0. If your determinant is less than 0, you get a saddle. If the determinant actually is 0, that's here, that's these two cases, you get these lines of unstable fixed points. So there are 5 sort of structurally unstable types of systems. They're the ones all along these curves because if you change the coefficients just a little bit, you change the nature of it, right? So to have this picture here, you need to have a 0 eigenvalue. If the numbers in your matrix change just a little bit, that might turn into a source, it might turn into a sink. That becomes important when we start dealing with nonlinear systems. So that's the end of this one.